Hey everyone, welcome back to the channel. Today we are building a 4-router ring network in Cisco Packet Tracer completely from scratch, step by step. Over the next 10 minutes, we are not just going to drag components around and blindly paste commands into the command line interface. We are going to explore the core networking principles behind every single step, from physical layer cabling choices and IP address efficiency to classless dynamic routing and convergence testing. Let us start with our physical layout by dragging our devices onto the Packet Tracer workspace canvas. We bring in 4 Cisco 2911 integrated services routers and arrange them in a balanced square topology on screen. We will place router 1 at the top left, router 2 at the top right, router 3 at the bottom right, and router 4 at the bottom left. Next, we drag 4 generic PC hosts onto the workspace and position one next to each corresponding router. Now let us talk about layer 1 physical connections and wire these devices together using the correct cable types. Ethernet standards dictate that when you connect two dissimilar networking devices operating at different OSI layers, such as a host PC and a router interface, you use a copper straight-through cable. So, we connect each PC's fast Ethernet port directly to its local router's gigabit Ethernet 0/0/0 interface. However, when connecting two similar network layer devices together, such as router to router across our WAN links, standard Ethernet requires a copper crossover cable so that the transmit pins on one end line up directly with the receive pins on the other end. We wire router 1 to router 2, router 2 to router 3, router 3 to router 4, and router 4 back to router 1, completing our physical ring topology. With the hardware cabling in place, let us configure IP addresses across all interfaces and execute the no shutdown command. By default, Cisco router interfaces are shipped in an administratively down state as a fundamental security measure. If an active port is unconfigured, it should not be capable of processing traffic. When we enter interface configuration mode, assign an IP address, and type no shutdown, we are instructing the router software to power up the physical layer circuitry and enable the data link layer protocol. Look closely at the Packet Tracer workspace. As soon as both ends of a link have IP addresses applied and no shutdown executed, the link lights transition from red to amber as span tree and link negotiations occur, and finally lock into a solid bright green. Green lights confirm that physical layer signaling and data link framing are fully established. Let us examine our IP addressing scheme and why subnet selection matters so much. For our point-to-point WAN links between routers, we do not use a standard /24 network mask because a /24 provides 254 usable host addresses. On a link connecting only two routers, 252 of those addresses would be completely wasted. Instead, we apply variable length subnet masking, or VLSM, using a /30 subnet mask, which is 255.255.255.252. A /30 mask creates a tiny subnet containing exactly 4 total IP addresses, 1 network ID, 1 broadcast address, and exactly 2 usable host IPs. This allows us to assign point 1 to one router interface and point 2 to the other, guaranteeing total address efficiency across our WAN links. Meanwhile, for our local area networks, each router gateway gets a dedicated /24 network address, giving each local PC its own unique broadcast domain. Now that our interfaces are up with green lights and proper IP addressing, let us shift to Layer 3 dynamic routing and configure the Routing Information Protocol, or RIP, across all 4 routers. To understand why dynamic routing is essential, consider what happens in a ring topology. If we relied on static routes, we would have to manually write individual destination paths for every single remote network on every single router. If a single link failed, traffic would drop until an administrator manually logged in to rewrite the routing tables. Dynamic routing protocols eliminate this manual overhead by allowing routers to automatically discover remote networks, calculate optimal paths, and adapt to network topology changes in real time. We enter global configuration mode on router 1 and type router RIP to initialize the routing process. Immediately after, we issue the version 2 command. This single command is absolutely critical. Legacy RIP version 1 is a classful routing protocol. Classful protocols do not include subnet mask information inside their routing update advertisements. When RIP version 1 sees our custom /31 subnets, it automatically rounds them back to their default class A boundary of /8. This causes catastrophic routing loops and summaries in modern subnet networks. RIP version 2, on the other hand, is classless. It carries the full subnet mask alongside every advertised route payload, ensuring our /31 links and /24 LAN subnets are interpreted with total precision. Next, we type no auto summary under the RIP routing process. By default, Cisco IOS attempts to automatically summarize subnet routes at major network boundaries. If router 1 sees multiple 10.0 subnets, it might try to summarize them into a single broad Class A advertisement before sending updates to neighboring routers. Disabling automatic summarization with no auto summary forces RIP version 2 to advertise the exact, unsummarized subnets as they actually exist in our topology. Finally, we publish our connected networks into the RIP update process using the network command. The network command in Cisco RIP serves two distinct purposes. First, it tells the router which local subnets to include as payloads inside outgoing routing updates. Second, it tells the router which local interfaces should actively send and listen for RIP update broadcasts or multicasts. On router 1, we type network 10.0.0.0 to cover our /31 interfaces, and network 192.168.1.0 for our local area network. We then repeat this exact configuration pattern across router 2, router 3, and router 4, adjusting only the local LAN network command on each router to match its unique /24 subnet. With RIP version 2 configured on every router, the network enters the convergence phase. Convergence is the state where all routers on an internetwork have exchanged routing information, processed remote advertisements, and agreed upon a complete, accurate map of the topology. RIP version 2 routers send periodic multicast updates to address 224.0.0.9 every 30 seconds. Within a minute of completing our configuration, every router's routing table has populated with distant subnets learned from its ring neighbors. Let us transition into testing and verification to confirm that our control plane and data plane are operating flawlessly. We open the CLI on router 1 and execute the command show IP route RIP. This command filters our routing table so we can inspect only the routes dynamically learned through RIP. In the output, we see routes prefixed with the letter R. Looking at distant LAN networks, we observe something fascinating about distance vector metrics. RIP uses a single metric to evaluate path preference, hop count, where each traversed router equals one hop. For router 1 to reach router 2's LAN or router 4's LAN, the metric shows as hop count 1. But when looking at router 3's LAN on the exact opposite side of the ring, router 1 sees two distinct paths that both equal a hop count of 2, one going clockwise through router 2, and one going counterclockwise through router 4. Because both paths have an identical metric, Cisco IOS automatically implements equal cost multipath load balancing, inserting both next hop destinations into the active routing table. Now let us execute end-to-end data plane testing directly from the host level. We open the desktop tab on PC 1, launch the command prompt, and issue a ping command to PC3 across the ring at address 192.168.3.10. The first ICMP request packet may briefly time out while Address Resolution Protocol, or ARP, resolves the hardware MAC address of the local default gateway. Immediately following that initial ARP delay, we receive 4 consecutive, successful ICMP echo replies with low latency, proving complete Layer 3 reachability across our entire multi-hop ring network. To trace the precise physical path our packets are traveling through the ring, we run the traceroute utility by typing tracert 192.168.3.10 in the PC1 command prompt. The output clearly displays every layer 3 hop along the path. Hop 1 hits our local default gateway at 192.168.1.1, Hop 2 jumps across the /31 link to neighbor router 2 at 10.0.12.2, and Hop 3 delivers the payload directly to destination PC3. To wrap everything up, in this lab, we successfully built a 4-router ring topology from the ground up. We applied proper cabling standards, enabled our ports with no shutdown to bring link lights up to solid green, eliminated IP waste using /30 VLSM addressing, enforced classless updates and explicit subnetting using RIP version 2 with no auto summary, and verified full end-to-end routing convergence through ping and trace route diagnostics. Thank you so much for watching. If you found this breakdown helpful, be sure to hit that like button, subscribe to the channel, and drop any questions in the comments below.